Hello, this is Dr. Kozhanov, and this is the eighth and the last lecture in the introductory course of Magnetism and Magnetic Materials that I teach at Georgia State University. So, today's lecture, we will talk about applications of magnetism, and it is common that most of the applied magnetism is called spintronics. So where can you apply magnetism in real life? Number one application is what we already talked about, and I already showed you in one of the previous lectures that we can store information, which means that if you have a magnet of certain geometry, if it has easy access, then there would be an anisotropy. Or it might be more than one easy access, but uniaxial anisotropy is something that's mostly used in information storage applications. And in uniaxial anisotropy implies that magnetization can be pointing either one way or another way along the easy axis. This is easy axis. So with that, you have a certain angular, and this is energy as a function of, let me use theta. Now this is theta. Theta would be the angle of magnetization with respect to easy axis. So if we are aligned with easy axis, so this is would be 0 or 180 degrees anti-aligned, then we would have a minimum of energy. And in the middle at 90 degrees there would be maximum of energy. We already saw that. And that means that the magnetization either wants to be aligned with easy axis or anti-aligned with easy axis. Intermediate state with magnetization either pointing at 90 degrees to the left or to the right is high energy state, and it's unstable. This is unstable equilibrium. The system wants to be either here or there. So it wants to be either a spin up or magnetization up or magnetization down. So as I said in my previous lecture, it's common to say spin up, spin down, and we are not implying electron spin, but rather referring to the magnetization. So if you have a magnetic element that can encode these two states, then we can say that, okay, spin up is a logical 0, or spin down is logical 1, or vice versa. We are to define that. And what it means is that we can store digital information in this. So one nanomagnet or a certain area of a nanomagnet would correspond to a data bit. And what you can do is that there are several options. Either you can make individual nanomagnets and put them close together, as close as you want. Closer together, that means that there would be higher information density. So more of them, more information can you store in this device. And at the same time, if you put them too close to each other, so if you have one nanomagnet and the other nanomagnet too close, then if you magnetize this one this way, it would produce magnetic field that would influence the other one, and they would be locked together. So they should be spaced out that the field originating from this magnet is weak enough not to influence the other state. So the field produces energy should be below this energy barrier from the neighboring area. The other option is to get a continuous film, and I'm drawing a disk. And the idea that you can spin the disk and you can write your magnetization here, and that means that if you take a cross section of this disk and look at this disk area, so disk is typically made of aluminum, it is light and it's easily machinable, and on top of that disk, let me use different color, some dark color with a small size. On top of that disk we deposit a magnetic film, and that magnetic film can be magnetized either up, oh that's not a very good color, but either up or down. And information can be stored in form of magnetic domains. We discussed that. And domains can be stable. There is a certain area between domains, as you remember, the domain wall. So domain walls are limited to, if you depends on the film that you use, but you calculated the domain wall width, and typical width are, let's say, 10 to 40 nanometers. And it depends on the material, it depends on the thickness of the film, so it can be optimized. But it means that the closest you can write 2 data bits. Closest separated, the closest placement of these 2 domains would be around 40 nanometers, and that would limit the density at which you can write this data on the hard disk drive, and that's what is used in computers to store data. So this is the limit. In order to reach that limit, we have to be able to apply local magnetic field, because if you want to write the information in this area, you have to apply magnetic field that is, let's say, pointing up, but it is very strong in this area and it falls off very rapidly to the sides, which means that it has to be concentrated. And also you have to be able to read this magnetic field, because magnetic field produced by this domain, it goes, as you see, it goes up. It's a dipolar field of magnetic dipole. It points up here and then goes down from this one. It can be up or down, but anyway, you have to be able to read magnetic field in this area above. There are certain mechanisms that can be used, and we will discuss one of them later in this lecture. So the other interesting recent development, let's say by recent I say in the past 10 years, and it's a rapidly developing field, are special materials. So it turns out that if you engineer a material, let's say one of those materials is cobalt platinum, but you should take this material, you should make a very thin film. Very thin film means that the film thickness should be in order of 5 nanometers. So it's several monolayers of cobalt platinum. And cobalt platinum, in this case, I would rather say that it's not cobalt platinum, but it is cobalt platinum, but not an alloy, but it would be rather having cobalt layer followed by a platinum layer. And these are extremely thin, so you can put less than 1 nanometer of cobalt. And to relate it to interatomic distances, there are typically 3 atoms per nanometer. So that means that you take roughly 2-3 monolayers of cobalt and then cover it with 1 monolayer or 2 monolayers of platinum. There are different approaches. So what that happens is that cobalt interacts with platinum. First of all, for thin cobalt films placed on a different substrate, this is substrate. No, you can't have these thin films in the air, so you always have a thick substrate, relatively thick, like aluminum and hard disk drive, or silicon, or something, or sapphire. You put cobalt on top, and because of the interaction with the substrate, it induces crystalline anisotropy, so cobalt becomes magnetized out of plane. And that allows writing the information in out of plane. So if you remember, the shape anisotropy forces this film to be magnetized in plane. It is a thin film. So if you go back and look at the demagnetization, you will see that the easy axis would be in plane. But if you put this thin film on a substrate that would change its lattice constant, you will induce crystalline anisotropy. And crystalline anisotropy will force it to be pointed up. This is called perpendicular magnetic anisotropy, or PMA. So now let's go back to this cobalt platinum system. If you'll take cobalt, zoom in, cobalt film on top of platinum, what happens is that you have 2 cobalt atoms right here, and cobalt is ferromagnet, so they want to be ferromagnetic like this. But there is a platinum atom right here. So what happens is that cobalt interacts with platinum. There is an electron bond here. And platinum interacts with two cobalt atoms. And what happens is that through the interaction, turns out that if they interact through the platinum, electronic interaction. Remember the manganese oxide, you have manganese, you have oxygen, you have manganese, and two manganese atoms interact through oxygen, and that forms antiferromagnet through the super exchange. So a similar interaction can happen here. So first of all, they interact with each other directly, but at the same time they interact through platinum. And when they interact through platinum, let's say this has spin as I, this has spin as J, spin or magnetic moment, it turns out that besides our exchange interaction and exchange energy, there will be more as J as I as J, and if you'll take these two, there will be dot product. Besides this, there will be this interaction through the platinum, and it has a name that's abbreviated DMI, and it's proportional to D as cross as IJ. So, and this is the constant of this interaction, similar to that. So you see dot product. Dot product is 0. So let me use different colors. So for this one, we prefer either aligned or antiferromagnetically aligned magnetization states, because dot product has maximum when vectors are parallel or antiparallel. Dot product is 0 when they're perpendicular. Here we have a cross product, which means that this interaction favors perpendicular magnetization alignment, and that is very unique. Now DMI. I had a graduate student who was studying this effect and she couldn't pronounce it. So let me see. This is N. I'm not pronouncing it on purpose. Interaction. So there were two scientists with last names, this and that. So I would ask you to pronounce this. Well, Zeloshinsky-Moria interaction. Zeloshinsky-Moria interaction. Zeloshinsky is a Russian last name. Moria, I think, is a Japanese guy. So they proposed that there should be an interaction existing in solids that favor this perpendicular alignment. But it turns out that it is very weak, and it happens at interfaces. So you have to have this interface interaction. Well, not only at interfaces, there are special materials that favor this interaction, but you can also have materials made of layers and have interaction through the layers. And in this case, if you have DMI interaction, I stands for interaction, but everyone calls it DMI interaction, then it favors this alignment, perpendicular alignment of magnetization, while exchange interaction favors parallel. So since two atoms interact between each other through the exchange, let me color code it. So let's say we will have direct interaction through this between atoms, and we will have let me choose for example, well, it's too bright as well, well, it's highlighter, so we highlight this interaction through this. Then the actual magnetization state would be something in between. Now, why is it interesting? So you know that if you have exchange interaction highlighted in yellow, then you'll have ferromagnets, antiferromagnets, ferrimagnets. Now, what kind of alignment you have if you have this? First of all, this interaction is still strong and you still have a ferromagnetic interaction, ferromagnetic alignment. They still will be aligned. But the question is that what this other term would give us. Let me show. Okay, So if you have just magnetized state, it will be magnetized ferromagnetically, either magnetization up or down as usual. But if you switch these films, what happens is that imagine that you have a domain wall. So you have magnetization up, magnetization down, and a domain wall here. Domain wall. In the middle of the domain wall, you might have different Neal or block type domain walls, but what happens is that in the middle you will have your magnetization either pointing this way, or it might be pointing that way, or in the opposite direction. So depends on the domain wall. But so what happens is that imagine that you are switching the magnetization. So what it means is that this domain wall is not stable, and how thick you can make this domain. So there should be another domain wall switching back to this area. So let me highlight. So these are let me increase the size. This is one domain. This is the area pointing up, and this is the area pointing down. Let me highlight it green just to get the really bright color. Okay, so this area points down, and we are having domain walls switching. I'm drawing this kind of a domain wall. So we rotate that way, there, and here we continue this rotation this way and there through the domain wall. Now, if the size of the domain is very small, then this domain becomes non-stable and it vanishes. So if you don't have DMI interaction, because having magnetization at 90 degrees is not energetically favorable for exchange interaction. So if you look up here, here is our exchange interaction. It favors parallel or anti-parallel alignment. So if you have, this is the reason we discussed that domain walls have a finite width, because magnetic moments want to be parallel or anti-parallel, and domains form because they want to stabilize, to minimize magnetostatic energy. Okay, now if you have material in which we have an interaction, DMI interaction, which favors the perpendicular alignment, then this, even a very small domain, becomes stable because it is surrounded with these magnetic moments that are perpendicular to it. So what happens is that Zeller-Shinsky-Maria interaction in materials or in thin films, and in this case where we have two layers of cobalt and platinum, it can be called interfacial Zeller-Shinsky-Maria interaction. So two atoms interact through the interface, and actually to get that interaction, you see platinum is a heavy metal, so there is a strong spin orbit interaction, and that basically gives us very strong very strong, fairly strong, let's put it that way, strength of this DMI. So what happens is that we are able to stabilize a very small domain structures. So if you would make domains less than, let's say, 40 nanometers, they would vanish, they won't be stable. But in these materials, we can stabilize a very small domain sizes. Why is it important? Well, if you write down the memory, you can write your memory, instead of writing that into 40 nanometers, you can write it into much small structure. Now here is simulation of these type of domains. So there are two ways the type of domain can happen. You can see that surrounding area here, this area is magnetization pointing up. And this is a small domain, and you can see that this domain can be extremely small. So the typical sizes of this domain can be 1-2 nanometers. 1-2 nanometers is a very small size. And you can see that the magnetic moment in the middle points down, this in blue, and here is your domain wall, 1, 2, 3, 4 spins apart. 1, 2, 3 atoms is 1 nanometer. So you have 1, 2, 3, 4, 5, 6, 2 nanometers. This area is roughly 2 nanometers in size. And it points down. Now this is needle type of wall, this is block type of wall, where the rotation goes around the axis. So you go from spin up, going into the swirling type of vortex state, and goes into the spin down state. So what DMI interaction and these special engineered materials make possible is, instead of having your domain size in the 40 nanometer range, you shrink it down to 2 nanometers. So what it means is that we are 20 times smaller. We can write down information into the area that's 20 times smaller, and it would be stable there. So what it means is that we can make data storage that is 20 times more dense, or let's stick to orders of magnitude, 1 order of magnitude more dense than available now. So instead of having 10 terabyte hard disk drive or 1 terabyte hard disk drive, you would have 10 terabyte hard disk drive or 100 terabyte disk drive. So factor of 10 is a lot, and there is a lot of interest in physics because these particles, so you can treat this as a particle, they can move through the lattice, and it is a very interesting physics, but application wise, that's data storage. Okay, so now this is this storage is something that's being developed now, and you won't see that on the market probably in the next 10 years or so. So this is a cutting edge research that's happening now in the laboratories. Okay, now this is information storage. Now let's talk about dynamics. We discussed it in the last 2 lectures. So and there are several things that I would like to point out. So again, this Landau-Lifshitz equation, I'll write it. Minus gamma m cross b. Now dmdt is actually this part here is the torque. This way, torque. Torque is m cross b. Now, if you look at the magnetization, this is the Landau-Lifshitz equation, and we added damping last time. So damping was minus alpha gamma gamma alpha saturation magnetization m cross b. Mu naught went to B. So if you notice, there is no mu naught here, it's in the B, and there is no mu naught here, we write B. So this is actually another torque. So you can see this is m cross B is our torque, but we do another cross product, and this is damping term. Alpha is damping constant. You can listen to my previous lecture. So if we look at this torque, so here is magnetic field, B. Here is the magnetization M, and this is the circle. If you would have only this term, the torque here is basically tangent to this circle. So it points, no, it doesn't look right. So where should it point? It should point there. So this term is this torque. Now, if you look at this term here, m cross b, then you will see that this torque, if we draw that circle through the magnetic field, this torque points that way. Basically, the red torque corresponding to m cross b makes the magnetization to precess around the field, and this torque along the green line is a damping torque that pushes magnetization towards the magnetic field. And you can regulate it by choosing different materials, and you can change alpha by changing material properties. And what happens is that this is B is in the z-axis. I will write BZ, but there is also X and Y, and I plotted it last time. So you have this precession, and it spirals towards the magnetic field. So x, y. Torque from the first term causes it to precess. Torque from the damping causes it to spiral towards the magnetic field direction. Okay, so this is, and alpha sometimes, its dimensionless constant, so it can be like 0.1 or 0.01 or 1. It's called also sometimes Landau-Lifshitz damping parameter or Gilbert damping. Okay, now let's move to interesting part. So as you know from the solid state physics, so atoms have certain energy levels. And if we put two atoms so closer together, so let's say this is interatomic distance A, and this is 0, means that we put two atoms closer together. When atoms are separate, and this is energy axis, and they have electron energy levels. When we bring atoms together, two electrons cannot sit on the same level. Electron from atom 1 and atom 2 cannot have the same level. So what happens is that when you bring many atoms together, these levels broaden to allow having particles sitting next to each other. So instead two identical particles cannot have the identical energy state, and therefore these levels, the energy states, move up and down, and they broaden into energy bands. So that can happen like this, like that. And now if you look into the energy bands, you will see allowed energies here. Let me do small eraser, right? Erase this part here. Oh no, it doesn't let me do that. Let me do more careful. So there is an allowed energy states here, allowed energy states there, and allowed energy states there in the material. So as we bring atoms closer together, what we have is we have energy bands, and there is also areas that are called gaps. Now, if you look at state density, then within a band, let's say you have allowed electron states here, you will see that energy as a function of density of these states. It can be different, but sometimes it's drawn this way. Now, we already discussed Fermi energy. If you have Fermi level somewhere here, EF, then the electrons are filling all bands below the energy state. So there are electrons only up to the Fermi level. And that's at 0 temperature. Of course, at higher temperatures, you have higher energy electrons. What it means is that if you have energy, certain energies, then you have electrons that fill this energy band only to the certain level. This is like inverted, rotated that. Let me draw it in a different way. So let me draw it this way. So we have energy. This is energy as a function of density of states. Density of states is how many electrons you have per state, or how many electrons you have per energy interval. So now, if this is the Fermi level, EF, and you have a band, let's say that is like that, then you fill the lower part of that band with electrons, and this part of the band has no electrons. And let me scroll down. So this is our band, but now we plot this not as a function of interatomic distance, but as a function of density of states. So it means that there are electrons there. Now it turns out that because of this exchange interaction, you might have spin up and spin down states misaligned. So what it means is that this state would be completely full, while this state would be half full or some partially full. Now, what I drawn here is, let's say this is spin up state of electrons, and this is spin down state of electrons. Notice this is Fermi level, which means that if you have a metal with electrons moving, this would be these electrons and these electrons that would define the conductivity. So this difference is called exchange splitting. So exchange splitting. Which means that if we have a conductive magnet, then electrons that conduct electricity, there will be more electrons with spin up, fewer electrons with spin down. So typically S-band states have higher mobility than D-band states because we have much lower effective mass of the S-band. And minority band electrons scatter more readily from the bands to the D-band. So idea is that you have minority states that scatter more, there you have majority states that define the conductivity. What it means, then if you have a conductor, then you have, so if you have a conductor piece of material, which is magnetized, let's say this state, then electrons in there, in this conductor, they scatter off these magnetic moments, and they're more spin up electrons than spin down electrons. When there are more electrons of one pointing in one direction, this is called majority band, and this is called minority band. And majority and minority means that majority is usually corresponding to the magnetization of this ferromagnet. So if you look into the current flowing through the ferromagnets, then you will see that inside of the ferromagnets you would have more electrons with spin up state. Now let's apply that. Let's make a structure. So imagine that you have a conductor where you have something metallic non-magnetic like copper non-magnetic, and you have magnet and copper, and this is, for example, iron or something like that. So let me draw a really thick magnetization here. So imagine that you have this iron magnetized that way. Your electrons move through this material. At the same time, in copper, there is no difference. In copper, there is the same, it's non-magnetic. So there is no difference between spin up and spin down. There is equal number of spin up and spin down electrons. In iron, there is difference. So what it means that if you drive current through this iron, and this is electron flow, so the current I should be flowing in the opposite direction. So what happens is that for minority, let's say spin down states, they're minority, and let's say majority is spin up. So this is minority and this is majority. Minority means majority. There are more electrons corresponding to spin up states in iron magnetized that way. So this arrow is our magnetization. Let me draw it more carefully. Magnetization. So what it means is that both electron up, spin up, and spin down will flow through the magnet, but there is more conductivity for spin up states because there's a majority. There are more electrons of that kind in ferromagnet. So what it would mean is, it would mean that there is a fairly small current flowing for majority states, and there would be fairly large current electron flow for majority states. So if you look at the conductivities of these two channels, so you can think of having two parallel resistors. So you would have resistor 1 and resistor 2 in parallel, and this is equivalent circuit for this. So that would be low R for spin up and high R for spin down. What it means is that conductivities in ferromagnetic conductors are different for majority and minority, and there would be more spin up electrons flowing out. So that means that there will be more spin up electrons here flowing from the iron into copper than spin downs. So in ideal ferromagnetic conductor, we would have absolutely no minority spins. We would have only electrons with spin pointing up flowing through iron. What it means for the current is that when you have a material, let's say this is metal and this is ferromagnetic metal. This is regular metal like copper. So you would have your current spin up and spin down, up and down. These are electrons. These are not magnetic moments. These are electrons flowing that way. If you look at the current, there would be electrons flowing into that, but when they come into the ferromagnetic, let me use this color again. When they flow into the ferromagnetic metal, what happens that this metal allows only spin up in ideal case, only spin up electrons to flow through. So what happens with other electrons? Well, they don't flow through, they are getting reflected and they sort of accumulate here. Well, we apply potential difference, so for electrons they don't quite flow back, but they accumulate in this. So majority spins aligned with magnetization are preferentially transmitted and minority spins are preferentially rejected. Now if you look at the other side of this, then we have a electron. These are electrons. Electron. These are free electrons that form the current. When these electrons flow from ferromagnetic metal into normal metal, into another metal, what happens is that they just flow through and you have current with electrons polarized in one direction. So ferromagnetic conductors are relatively permeable for majority spins, and they're impermeable for minority spins. And if that's ideal metal, that would be the case. In real life, there would be some percentage of minority spins transmitted as well. So where we can use that? Well, if you would like to have an area, let's say, if you would like to have a film, you can induce electrons that are magnetized only in one direction. So what you do, you put on top of that metal, this is a, now let's say copper sheet, a thin film of copper. So if you put on top iron and magnetize it, let me use a smaller but still fairly thick film. So let's say you magnetize your iron in this direction, and let's say you make one contact here, and that might be ground, and other contact to iron, and let's say plus, no, minus voltage, plus voltage. You supply electrons, minus voltage. So you drive electrons through iron into copper. The current flows through the iron into the copper and to that electrode. So what happens is that in copper you will have electrons that are aligned with the ferromagnet, and these electrons would have only one direction of magnetization. Of course there are thermal fluctuations, of course there are scattering processes in copper, and in this case the spins of electrons will change their direction, but still there will be more spins of one direction flowing because we constantly would supply them from iron. Now let me erase this. No, let me erase this in a way that won't take too much of my time. Okay, good. So now let's look at this structure. If we look at how many magnetized electrons we have with a spin, let's say, pointing up and down. So there is this area, there is this area, and we are flowing electrons. So there are electrons of various signs flowing in, but we reject electrons, spin down electrons, which means that there will be more electron with a I will go beyond that and I will scroll. Yeah, there would be more electrons with a negative sign. Then, as we go through the ferromagnet, there would be more electrons with positive, with a spin-up state. And as we go into the conductor, there would be a certain decay of having electrons. So this is spin-down state, this is spin-up. And vertical axis is, you can think of spin magnetization of this area, because besides the magnetic moment here, there are also the spins of electrons that contribute. So, and you have this with this kind of situation, so that if you turn off current, everything will equalize. There will be spin up electrons here, but at the same time there will be no accumulated electrons there in thermal equilibrium. So this is non-equilibrium spin polarization. Spin down accumulates before the magnet, spin up accumulates after the magnet. And this is near the interfaces. Okay, now if you look at this process, let's look at this process again. So you have this boundary, and imagine we were sending electrons having a particular spin. Then what happens if you send, this is our ferromagnet right here, M. So what happens if you are sending spin that is not aligned with that? Would it be transmitted or reflected? So for that we have to go to quantum mechanics. So basically spin at a certain angle, theta, can be represented as certain alpha of spin ups plus beta of spin down. It is sort of a mixed state of spin up and spin down, where alpha would be cosine theta over 2 and beta would be sine theta over 2. Theta would be angle, this theta. So in quantum mechanics we use probabilities. So there will be certain probabilities, and probability that spin is up is proportional to alpha square, probability that spin is down is proportional to beta square, which means that an arbitrary spin state is a superposition of spin up and spin down states, quantum mechanical states. And that means that there will be certain probability of transmitting and reflecting. Now let's look at this. So let's drive current through this system and see what is happening. So imagine that you have electron with a certain spin, it doesn't really matter with which spin, going towards the interface with the magnetic. This is magnetization. I should use red to be consistent. To the ferromagnet. This is ferromagnet, this is metal. What happens is that when this electron transfers, so if you look at this, it is a superposition of spin up and spin down states, which means that spin up state would go through, and spin down portion of that would reflect. So what it means is that we had this type of electron tilted, and when it reflects, it basically part of it goes through, part of it reflects. Now how do we get this type of spin? Well, we can put another magnet here, right? So we can basically have this. So let me highlight it. Let me highlight it in a way that won't interfere. So two magnets. One is magnetized vertically, other one is magnetized at an angle. So when we have magnetized at an angle, all electrons that are coming through exit magnetized at an angle. So we don't care about what's happening here. So let's look at this. So this is our copper. This is copper, and this is iron. This is iron. So we magnetize electron, and it scatters. So what happens is that here at this interface, when this rejected electron reaches this interface, part of it will go through aligned with this magnetic moment. The other portion will get reflected, but now it will get reflected and having the magnetization. So you see, this electron going to this interface had spin down. After this interface, it has tilted spin down. So what we can, I will get back to that image. Let's keep it there. So what we have is we had electron down and we did something to it and we got electron tilted down. These are, I'll highlight. This down is this one and tilted is this one. So you have to really apply torque to that electron, and torque pointing in this direction. So this is delta torque. You apply torque in that direction, and that tilts electron. So what is happening is actually you can think of these metals that first of all be ferromagnetic metals, polarize electrons. But also what we do is actually we have electrons incident in, and we rotate the reflected electrons. Now, if you think about where this torque goes, well, it should be applied to something. We are in we have a situation where we don't apply just torque. That torque, if you look for Newton's third law, action-reaction pair. So now if you look at this red vector, so we had red vector tilted at a certain angle. To that vector, we actually apply that torque, but in the opposite direction. So positive torque is applied to electrons, negative delta T, delta tau. Negative torque is applied to this magnetization. So we apply external torque to the magnetization, and that forces that magnetization to tilt. A little bit, not much, you won't notice it here. The reason why is it not tilted is that we have damping. As you remember, let me scroll up quite a few slides. We have this term here, which is also torque, so we can describe this as a damping torque, right? This term. And this term, while electrons scattering of magnetic moments apply torque, if you don't have too many of them, the damping doesn't let the magnetization to turn. So if you look at this image, we add actually damping counter, so torque damping. That doesn't let the magnetization to rotate, and that's in low current. Low current. So one electron doesn't do much, but if you have too many of these, if you have too many of these torques, imagine that you don't deal with single electron, you have many electrons scattering of this magnetic moment. What can happen is that this delta tau would overcome the damping, and that would cause our magnetization to rotate. And in this case, for high current, Let me erase this to be more clear. For high current, our magnetization will tilt. It will tilt. So there would be, if you had magnetization M here, tilted at an angle, here we'll have M plus delta M. So it will tilt. What it means is that it's not that we are only the scattering processes polarize electrons. When electron gets reflected off magnetic material, if you have many of them, they apply torque to that magnetic material and they rotate that magnetic material. So this part, we use it to polarize electrons, and this is called polarizer. And basically, polarizer reacts to electric current by changing magnetization to a certain angle, and it is unstable state. Okay, so what we can do now is we can look at the dynamics, how this magnetic moment here moves. So as you remember, we have a magnetic moment. We magnetize it, so we do apply magnetic field B in vertical direction, and it rotates around it. There is torque that forces it to rotate. There is damping torque pointing it this way, tau damping, that forces it towards it. Now we send electrons, and these electrons apply torque, but in this case this torque is applied in this one. So this there was a guy whose name was Slonchevsky, last name, but some call it Slonczewski. A typical Polish name, so I would say Slonczewski, but following the English rating, Slonczewski. So the torque, this torque here, imposed by electrons, can be written, there would be certain constants, to E delta ms, an important part, m cross mf. So that is basically what we do is we send electrons through this. This is our MF magnetization, and MF roof, this MF roof here is basically a vector, unit vector pointing along this magnetization, indicating the direction of polarized electron, and M is this M magnetization of this vector. So this is called Slonczewski torque term, and if we use that Slonczewski torque term, you can write our Landau-Lifshitz Gilbert equation with the torque term. That would be, as usual, gamma m cross b. I won't write vectors, I will imply vectors, minus, there should be minus there somewhere, minus alpha gamma ms square m cross b, and plus constant, that constant m cross mf unit vector. So this term is, let me choose different size, is responsible for this motion, for circular motion. Then this term here is responsible for damping, that we return our sample back. And finally, this term here is responsible for magnetization knocking off equilibrium. So what it would mean here is that if you just drive no current through this interface of ferromagnet, let me draw it again. So we have iron, iron, spacer copper, copper, copper. So if you drive current through it this way, current this way, electrons flowing that way. So if you drive current through this and look at the magnetization of this particular iron here, then if there is no current, it would want to oscillate down to the magnetic field direction. And magnetic field, let me use the green color here. Let's say magnetic field is in this direction, H, in one of those. So if there is no current, this magnetization would spiral down to the direction of magnetic field because of the damping. Damping will push it towards the magnetic field. When we drive current, we will apply torque that points in the opposite direction. And that torque would want this magnetization to be flipped. Now this is called spin torque. So spin torque, the devices where you have two ferromagnetic layers sandwiched in between copper layers with a copper spacer in between are called spin torque device. But what we do, we use electrons to transfer that torque, and that would be spin torque transfer. So spin torque transfer device, there are several things that we can do. Now, if you look at these torques, then damping in materials, what we can achieve is the following idea. What if you look at this? There is a possibility that when we drive current, the torque that we apply would compensate the torque of damping, and we would be able to achieve steadily precessing magnetic moments in this material. So we will pump energy by the current. And in this case, you'll have steady precession of magnetization. If you look at this, so we need to torque, spin transfer torque. So STT, spin transfer torque. If you want spin transfer torque equal to negative damping torque, then we would need to drive, if you look here, oh, by the way, this J is the current density, J. Let me use small j for that, so it won't be the same as an exchange constant. So J is a current density. So higher current density, more torque we apply. And to do that, you need certain current densities. And current densities, as Slonchevsky calculated in his work. By the way, this was work done in 1996 by Slonchevsky. You can dig up his paper. Current densities should be around 10 to the 7th amps per square centimeter. Is it big or not? Well, so if you take a typical wire with a cross section of you can calculate the current density to achieve this level. So if you have a diameter of 1 millimeter, and that's typical wires for used in our, then to achieve that current density, you should drive currents that are approximately 0.1 mega amps, 100 kiloamps. This is huge. At these current densities, this will melt and evaporate. Now, if you take a human hair, so as you remember, human hair sizes are 50 microns, 10 microns. So if you'll take a diameter of 10 microns, then currents to achieve this current density would be approximately 10 amps. Now, if we scale down it to wire size, even smaller one, with a cross section of dimension of about 0.1 or 100 nanometers, then currents would be approximately 1 milliamp. So while it is still huge current density, but at these sizes we can achieve these current densities at nanoscale. So we need to have a nanoscale wires, and that wire should be broken in 3 layers. So that is done in so-called spin torque nano oscillators. So in order to achieve this, people do very small structures, nanoscale structures. This is an example of this structure. So there are many interesting things, but if you look here, this is the very complex structure. So it's complex, but there are 2 important things. This is ferromagnetic metal 1, this is ferromagnetic metal 2, and it's separated. And there is another ferromagnetic, so it's pretty complex. But the idea is it's called spin torque nano oscillator. So spin torque nano oscillator is spin torque device where we compensate torque, damping torque by spin transfer torque applied by the current. So there are 2 magnetic metals, this blue and another blue with a spacer, and when they apply certain magnetic field, and they analyze the spectrum of this oscillating portion. And the result of this is the following. So this is the typical, oops, let me do it again. So this is the result. So you drive the current through the stack. By the way, there are 2 layers I forgot to mention. There is one layer that is just fixed in a direction, and that can be achieved by making it either thicker or thinner, or you can have more anisotropy by changing the composition. But one of the layers is harder layer, and other layer would be a softer layer, which would be easier to rotate, and spacer. And of course, on top and on the bottom, there are 2 contacts that used to drive currents. So fixed layer and free layer are, let me scroll back. So these 2, this would be called fixed. And it would be fixed, the magnetization would be fixed in a certain direction, and that would be a free layer. Free implies that this magnetization is easier to rotate, and therefore when we drive current, we apply sufficient torque to that. So what happens is when we drive different current, we apply different amount of torque, and we can achieve different frequencies at which we can oscillate this. And you can see these lines are oscillations at certain frequencies. So these are the frequencies at which our magnetic moment oscillates around the magnetic field. Now the interesting part of that is how do we measure these things? So if you go back here, you can see that there is a scattering. Even let's go back here. So you can see that if we have electrons aligned with magnetization, they go through. If you have electrons misaligned with magnetization, they reflect it. So therefore, if we have let me use this. If you have electrons that are aligned with a magnet, we have low resistance for this channel. If you have electrons that are misaligned, that point in opposite, we have high resistance for this channel. What it means is that if you have a magnet, let's say this would be our fixed magnet, and this magnet that would be free to rotate, I would put it in the 2 directions, which means that we can apply low magnetic field to rotate it. Then when this magnet and that magnet are aligned, then the current will go through with a low resistance, low R. If we align them in this direction, that would be high resistance. Now, how do we rotate this? Well, let's look at resistance as a function of magnetic field. and we will be applying magnetic field in vertical direction, so that would be H. When H is very high, pointing in the positive direction, that would be plus, and that would be minus H, this way and that way. When the field is high in the positive direction, both of them would be aligned pointing in this direction, and we would have low resistance state. And we reduce the field and both layers stay magnetized. Then we reduce the magnetic field until a certain level, and at that point, so this is free. So these two magnets are designed in a way that free layer has low coercivity, so Hc is low. And for this one, Hc is high. Two different materials. Or we can choose coercivities by changing anisotropy, by changing thickness of these layers. So it means that at negative field, the free layer will switch first. So it will switch first, and it will lead to high resistance state. And it would be high resistance state here, so we'll have fixed layer pointing up, but free layer will switch down until the fixed layer switches. So at some magnetic field, the fixed layer will switch, and we'll get into the both magnetizations pointing down. So again, when electrons, they are polarized, so electrons will have, let me choose different color. So let me use green for electrons. So electrons are coming in both directions that way. After this, they become polarized by fixed layer, and then they scatter. They either go through or they get rejected, dependent on the orientation of that. When they scatter, it's a high resistance state, and that causes high resistance. Now going back, let me double check that I have the correct width. Now we are in two spin down state. Now we go back, and both of them are magnetized in spin down state, and we apply positive field, and at a certain point we have switching free layer and then switching fixed layer. And this case is fixed layer down, free layer switched back up. So you see it has a resistance induced by the different orientations of magnetic. So there are two states, either high resistance state or low resistance state. This is called a giant magnetoresistance. So where we can use this? Okay, imagine that you have this device with a layer, fixed, free layer. Fixed would be black, free would be right, and you drive current through it. And imagine that you put it close to the hard disk drive, magnetized this way, that way, domains magnetized in various directions. So what would happen is that magnetic field originating from the stored data pointing in this direction. If this field, if this spin torque device, not spin torque, but this is already called GMR device. If this device is brought close to the surface of the hard disk drive, then this field of magnetic moment is sufficient to flip magnetization of the free layer. So what it means is that we are flipping magnetization of the free layer, and we go to high resistance state or to low resistance state, dependent on the orientation of magnetic moment. So in 2007, two people who basically discovered that effect, giant magnetoresistance, and this is Albert Ferd and Peter Grunberg. This is Peter Grunberg, and this is Albert Ferd. They both did a pioneering work in discoveries of giant magnetoresistance, and you can read about that. They got Nobel Prize in 2007 for this work. The beauty of this is that revolutionized the readout of local magnetic fields, and in particular readout of magnetic fields produced by the data stored on the hard disk drives. And all sensors of all readout devices that are inside of these hard disk drives are based on this giant magnetoresistance effect. So this is how you read magnetic memory. Now, the information storage is one application here, and the information actually can be combined. You don't have to have these separate layers of hard disk drive, and you don't have to have a separate layer of readout. So what you can do is you can make this stack having a fixed layer, magnetic layer, fixed in one direction, magnetized in one direction, and another layer which can be called free layer. I will put arrows in two directions indicating that it's free to rotate. That would be free layer. And when you drive low current, when you drive low current, you basically can measure the resistance following this. So when you drive low current, that current is not enough to produce this torque. So it's not sufficient to produce torque. It's low current. And you would basically use this current to measure resistance of this. So at low current, and you would basically, by measuring resistance, you will have either high level of resistance or low level of resistance dependent on the orientation of this particular free layer. So if free layer is pointing in this direction, you'll have low resistance, low R. If your free layer is pointing in that direction, you'll have high R, high resistance. So that two resistances can be your logical 1 and logical 0. And information in this case is stored in this free layer. Now, if you want to write this information, and this is read at low current. And if you want to write this information, you drive high current, high. So when you drive high current, let's go back to this picture here. When you drive high current, you drive high current densities through it. Your torque applied by the current is much bigger than the damping, and basically what is happening, let me illustrate that. So your magnetic moment, I will be tracing the point tip of that magnetization vector. It was oscillating, which way filled up. So yeah, so it was oscillating here. Then you apply current, so it would start to oscillate. And if you kill current here, if you reduce current, it will relax to that state. So initially your magnetization was pointing up. You applied current pulse. It applied huge torque, and it rotated it, and it oscillated to spin down state. So applying fairly high current pulses can allow you to switching. Switching at high currents. And if you drive current one way, you will switch it in one direction. So if you have electrons flowing this way, you'll apply torque from the fixed layer. If you drive current in the opposite way, you will switch by the reflected electrons from the fixed layer. So you either switch it one direction or the other direction. So what it allows to do is it allows to implement a memory which does not require separate contacts to write and read information. So now if you go to internet, and this is one of the examples, that's a Next Platform website, You will see that, and not only there are many companies which are developing memory, and you can see it's written spin torque MRAM. You know that operational random access memory in the computer, RAM. So that is a memory where you store all your documents before you save it, and that's where everything is stored temporarily while your computer is operational. So this is a very fast memory. Now imagine that power goes off. All information stored in memory, whatever document you didn't save, disappears. Because it's stored in the memory which is dependent on the power supply. Now, what we can do is we can use these devices to make memory, and the difference would be they would be as fast, they would be energy efficient, but the difference would be is that you store information similar to hard disk drive in a magnetization of nanomagnet. And in this case, this is called spin torque MRAM. M stands for magnetic. So this is a non-volatile RAM. So you can read through different papers, and basically this is different applications. So you can use it in different applications. So there are different graphs comparing the storage in different type of magnetic materials, but the spin torque RAM, and these are actual chip. This is actual memory chip that is currently produced. You can buy it. It's not in the computers yet, but it will be soon. You see, it's October 2019, and this technology was in laboratories in early 2000s. In 2010s, it was transferred to the companies, and it was the point where it was started to get developed in companies. And nowadays these chips are mass produced, and maybe you will see those on the market. So the advantage is that you can have your memory that is non-volatile, but it is as fast as a random access memory, and if power goes off suddenly, all information is still in the memory. It doesn't disappear, it's non-volatile. More than that, you can utilize these devices, you can connect them, interconnect them, and use them to perform logic operations. And that would be a totally different course on the Spintronics with a focus on logic devices. But basically, you can have your transistors based on these devices, not transistors, but similar devices that would do logic operations, and at the same time they would store the information, which means that you don't quite even need the memory to store what you're doing. Well, you actually do, but that is an advantage. So this is a cutting-edge research, and that is research currently done at universities. That is type of the research that is currently done at companies, and companies are actually producing this already. So advantage over the flash memory, that's memory USB cards, or how you call them, thumb drives, is usually thumb drives uses lots of energy. It stores information in magnetic charge, while these are storing information in the magnetization of the free layer. The information is non-stored, it's non-volatile, it can be stored, I wouldn't say forever, but long-term storage. At the same time, it's energy efficient. It consumes much less energy than your USB drives, and it is at the same time very, very fast. Okay, so now I would like to wrap up the course at the end of this video and say that let's see what we learned. This is the last class. Unfortunately, it went online. I would show you many different things in my laboratory that are related to that, because I do research related to that. But first, we review of magnetic field. We introduced magnetization, and we introduced magnetic properties of material and different relationships. We talked about experimental methods. And experimental methods to generate magnetic field, to measure magnetic field, generate and measure magnetic fields, to magnetize material, to measure magnetization, measure susceptibility or permeability. We talked about that. Then we went on to origins of magnetism, so atomic origins. We talked about multi-electron atoms, angular orbital magnetic angular orbital momentum, spin orbital momentum, total orbital momentum, and we talked how they add. And then we went on to interactions between I wrote spins, but actually J's. Interactions between magnetic moments in atoms, and we talked about dipolar interaction, exchange interaction. In today's lecture, we talked about DMI interaction, and as a result, we talked about different materials: diamagnets, paramagnets, ferromagnets, antiferromagnets, ferrimagnets, and we analyzed all these different types of magnetic materials, how they are different, what is the origin of this phenomenon. We talked about, in particular, we talked about a lot about these three, and about this one in it's a huge interest of ferromagnet. We talked about domains, domain walls, anisotropies. We talked about the different hard, soft magnets, their applications, and at the end of the course, we talked about dynamics. Magnetization dynamics, and as applications, microwave applications. Microwave applications are essential, and magnetic materials are essential because all this, if you look at these spin torque oscillators, look at frequencies, they're all in gigahertz range. So these are microwaves. And what it means is that this device here, it can be used to generate microwave signals. And that it can be tuned because you drive different current through the spin torque, you change the oscillation frequency. And it can be engineered to oscillate at different frequencies. Or we talked last time about ferromagnetic resonance and applications of that, electron paramagnetic resonance, ferromagnetic resonance. And some of you did presentation. I would encourage you to look at the magnetic resonance imaging. So that is another application of this dynamics. And lastly, we talked about spintronics. So Spintronics is the applications of magnetism that focuses on applications to store information and process information. So today we focused on actually not only that, spin torque oscillators and that produce the microwave signals are also applications of spintronics. So spintronics is abbreviation of spin electronics. So basically, mainly it focuses on information processing and doing computations with interacting nanomagnets, and you can send spin waves and encode information in a wave to let it process it. But Spintronics is not only focusing on information processing and computations, but it also focuses, let's say, the storage, information storage. So today we we looked at the information storage, and there are also computing. We talked a little bit about that, but this is a separate topic and we don't have much time to talk about that. Now, also there are these microwave applications. So in general, when people talk about spintronics, this is a just nice word describing all these applications. Okay, with this, I would like to thank you for listening to my course. Although it went online, I hope that you learned quite a bit from it. And if you're interested, there are many further things that you can learn. So you can, I would say that points 1, 2, 3, 4 And these are pretty, we did a lot. That was before we went online. And these topics we studied not too in depth, but pretty well. But what started after that, 5, 6, 7, we did a very overview type of lectures. So which means that we didn't stop in great detail on this particular material. There are many phenomena that can be studied in greater detail. You can use advanced math or quantum mechanics to study these interactions in magnetic materials and how they behave, how these domain walls move, and how the spin torque actual oscillator. We used classical approach with torques, but actually it's a quantum mechanical type of device. And there is a lot of leading cutting edge research in these 6, 7, 8 points of the course. All right, thank you everyone, and have a nice break. And you will still have to do the final exam, and you will see all your grades on iCollege, so follow iCollege. All right, bye.